Hello, it's Carly McAvoy. I want to talk about graph behavior for polynomial functions. And the most basic ones that you know before are linear functions, so it's to the first power. But look what happens when we have something to the first power. When we have something to the first power, we have a line. But when we have a positive lead term, remember the lead term is the first term in a polynomial, and that's determined by the highest degree. So in this one, this is a first degree and a 0 degree term, so this 2x is our lead term. That power of that, or the degree of that, determines what our graph looks like. In this case, it looks like a line. But the coefficient determines what's happening with that line, the end behavior. Since this is a positive 2, at the end of our graph to the far right, we're going to be rising. So that tells us that this graph is rising up to the right of that graph. That's what a lead term tells us. On the other hand, for this function, it's also linear because it's to the first power, but the lead coefficient is negative, and that means that we're going to be falling, or that's going to be heading towards the negative as it goes to the right. So that negative tells us it's going to be going to the negative. To the positive tells us it's going to the positive. Notice our y-intercepts. The y-intercept is this number at the end. -1, that's where we're crossing the y-axis. +2, that's where we're crossing the y-axis. Okay, let's look at a second degree equation. Second degree equation means that our highest degree is in the polynomial is a 2, and we can see we have the same basic shape, that is a parabola, but the lead terms here, one of them is positive, this being +1, means that to the right our behavior is going up. We're going up, and because this is an even power, we see the same behavior on both ends of our graph. That happens with even power, so they're both pointing up because of our coefficient. The degree tells us it's going to be a parabola, but the coefficient tells us it's going to be a parabola that's opening up towards the positive. Notice our y-intercept, -1, again, that's where it crosses the y-axis. I want you to see how the y-intercept is the same as we go through all these different types of graphs. Over here we have something that's a negative coefficient, therefore it's going down, and these two endpoints are going towards negative infinity. It is a parabola because of the second degree, but it's going down because of that lead coefficient. All right, third degree terms. Third degree terms have this different kind of shape. That's determined by the degree. So every third degree term is going to have this shape, but it's going to either be going up towards infinity or down towards negative infinity based on that lead coefficient. So in this case, the coefficient is 2. That's positive, so we know at the end to the right, we're going to be going up. Whereas when it's -2, to the end, it's going to be going down. Notice also that our y-intercepts are the same. -1 y-intercept crosses the y-axis at -1. Just like it did for our parabola or our linear equation. Over here, my y-intercept is supposed to, oh, yeah, it's different, sorry. I should not have said that, because with cubic degrees, we actually have a different thing for y-intercepts, but, oh no, I didn't. I just didn't type this correctly. This one, this is not the correct equation, right? How would I know? Because if y-intercept is when x is 0, so you have zeros all the way through here, the y-intercept should be 2. Somehow when I wrote this in, I did not write it correctly. That should have been a -1. So the graph I had was not the graph that I was showing. It is true that the graph was going down, so I know that it's a negative lead coefficient. Also true that it's third power, I can tell by the shape. But I could also tell that I had a mistake in there because the y-intercept should have shown there. All of a sudden I was thinking of a different kind of equation. So those remain the same. This one should have been a +2. Obviously, when I typed this in, I didn't type this in correctly. If it was +2 at the end, it would be crossing up here at +2. All right, the last two graphs that I want to show you are the fourth degree. This is fourth degree. It has a y-intercept of -1, so it's crossing here. A fourth degree, like a second degree, has the same end behavior, both beginning and the end. That's because something to the fourth power is always positive, right? So this is always positive And this 6 in the front is going to tell us what the end degree is. This is a 4th degree, and it does look a lot like a parabola, but it's flatter. It's actually a flattened out bottom here. So a 4th degree power looks like a parabola with a flat bottom, and then this 6 tells us it's going to open up in both directions. 5th degree starts to look like a 3rd degree, but it's also got more loops and flatnesses, and if we zoomed in on this, we'd see even more changes. In this one, I did type correctly the y-intercept of 2. You can see it's crossing at 2. I also know that even though this is my 5th power shape, and the shape for 5th power can look pretty different than that. I mean, there's 4 different bumps. It's hard for us to see all those bumps because I didn't zoom in that great. But what I want you to realize is the end behavior, that is this behavior down here at the end, is determined by the sign of that lead term. Lead term being negative means we're going to be heading down as we go there towards infinity. So that's how I can look at all these different kinds of graphs and know what their shape is by the degree of the lead term, and know what the behaviors at the end is going to be by the coefficient of the lead term. So down here I summed this up. Lead terms determine the shape of the graph. The lead term is the term with the highest power, but the lead coefficients determine the end behaviors of the graph. Also, polynomial functions are continuous. That means they don't start and stop and start again. I could put my finger down on a polynomial function and never have to, I could trace the entire graph without lifting anything. So that's what we mean by continuous. And they're smooth. That is, there may be loops and dupes, but there's no sharp points or sharp edges. So be prepared to answer those kind of questions on your homework about what is a polynomial function. And then the vertical line test is if you draw a vertical line, it should only touch a function at one point. So if you had a different kind of function that wasn't polynomial, we could still use the vertical line test. Think about a vertical line going anywhere down here. Even though this looks pretty vertical, it's actually not. Anywhere I draw a vertical line, it should only touch the graph at one point. If it touches the graph at more than one point, then it's not a function. So the vertical line test is very easy to check. Draw a vertical line, making sure that it's only going to touch your function at one place. So here, I did have a mistake in this video. Hopefully you remember that what I talked about. When I have the number at the end, +1 or +2, -1, that tells me where it's going to cross the y-axis. I had a mistake when I wrote this function out. Okay, have a fantastic day. I'll talk to you next time.